gặp lại em trước khi mình cách xa. Nửa quãng đời về sau anh không phiền em nữa, dù anh biết mình chẳng có cơ hội thay đổi em nữa rồi. Chỉ là anh nhớ thôi. Em muốn sự bình yên, anh quen cuộc sống vô định. Em nghĩ về tương lai, anh không nhiều toán tính. Anh có lỗi làm em thấy ưu phiền, để người thứ ba xuất hiện, rồi mang đi mất người quan trọng nhất. Trái tim đã mang tổn thương, sức em cũng đâu nghĩa gì. Vốn dĩ không là của nhau, thì nãy ở mãi bước đi. Ngày không em có dài, anh vẫn sẽ tồn tại. Chỉ là con khổ tâm, gương sáng trong âm thầm. Chắc anh phải cần thời gian ngắm đi cánh hoa úa tàn. Lá buông mận duyên trời ban, từ nay tình yêu vỡ tan. Lời làm mất em rồi, anh giống như kẻ tội. Ba người về hai lối, là chính anh có tội. Em muốn sự bình yên, anh quen cuộc sống vô định. Em nghĩ về tương lai, anh không nhiều toán tính. Anh có lỗi làm em thấy ưu phiền, để người thứ ba xuất hiện, rồi mang đi mất người quan trọng nhất. Trái tim đã mang tổn thương, sức em cũng đâu nghĩa gì. Vốn dĩ không là của nhau, thì nay ở mãi bước đi. Ngày không em có dài, anh vẫn sẽ ôm tại. Chỉ là con khổ tâm, gương sáng trong âm thầm. Chắc anh phải cần thời gian thì chưa tới. Yêu thì chưa tới. Okay, given an integer array nums and an integer k, return the k's most frequent elements within an array. The test case are generally second. The answer is always unique. Always unique. Okay. For solution, we can use an hash map to store all the numbers frequent element for each number, and then we can sort by the number of elements, and we return the result from this. Is one to take times complexity of analog n. That short algorithms gonna take analog n times this. Scales array. So for two, suppose with the number of array have n elements, so the max number of elements is for every when each element has just one element. So for the real ones here, frequent elements. So you have the least length nums. Count elements. For example, 1, 2, 4, 3, 5. Count element we get this count. For example, this we have simple. For this array, we're going to say for 1, 2, 1, for 1 we get 1, 2, we get 2 and 3. Okay, let's take another example here. 1, we just have 4 here. 4 this, so we're gonna take 4, just 1 and 2, for 3 elements. We have 3. So 2k elements
example, here we got report. Return result here. And how can we get all of these elements? Two, 3, 4. Machine okay, first we still have to create a map to store this element first. So comma here for nums range comma get this number not beginning to 0 plus 1. So for the proof of solution, at this step we gonna short this array, and it gonna take time. Complexity will be n log n. There are 3 things I never seen in my life. Here Nhau thì ấy đường ai nói đi, ai đã mất em rồi, em giống như kẻ tội. Vì chính em có buồn. I'm gonna use pocket shot, that. Okay, for be in range. First one. Frequent first for range now for names and cow. Names cow. The items sequence cow. Two names. Right. So to reroute here to anti-array. For range kg. J range. The last elements is range of names. So right here, frequency to J, if, and press equal to K return. okay with for the 8K, for example, we're gonna redo Rồi là mơ đêm rồi, em giống như kẻ tuổi. Out of range. See, there's one here. Em giống như kẻ tôi. Sorry. Okay, last element is here. Just comfortable. Okay, elements. Okay, add rounds. Okay. Frequent elements. Time complexity is gonna here, here, space, can get a port 2 using okay short. Okay, first we just still using a counter as well to return to turn the number of lines. Create sequence array that return the count for the for the count math with this number has this count, right? That it. And then we're gonna need a frequency. This array for range randoms. This one. And for numbers in comma silence with frequent car is append. We can use half. We can use cancel and as math here, or just an array. I prefer to using an array here. Suppose append number. So at this step we have to 3. So you're gonna get array that, and for this step we're gonna get 1, 2, 3 frequency. We're gonna get an hash model minus 3, 2, 2, 2, 2, and 3, 1. So for the last element, cast an array of this and this. For 3 we get 1, 2, 2, and we get 2 and 1. We got 3 here. So the working result here. J in range K. And frequency +1 and -1 to get the last element. go to the first element. Just go to the first element here, because this element always empty. This one, and so this an array, so we're gonna extend this array, array frequency J, and if the length of this response is going to be equal to k, we return the result, and not return yes. Ooh. I think someone else using Java or C here for better time complexity. Hip. Okay, so we still have push, and okay, it's short, it's kind of like short with a binary short. Okay. For the screen. Come on. Four. It's kind of like do some problem. 1, 2, 3, and the problem is I have to use I must use the one additional space, so okay. Do some program. Before for a better solution, we can use short first. Short. My short is 2.2. And this is gonna be n. O n times. Come on. Ash. This one is short, so okay, we can just using 2.2. So that right? No. And exact and valid solution. It's kind of like left, right equals to 0 and minus numbers for the last element. Right, left, we're going right. If number yeah. Some total is left is a number right. Yes, total return left minus 1 minus 1 I need it left shift to right. Left. Mouse. Okay. Ooh. Introducing it's kind of like this problem. Right. 1, 2, and minus 1. Minus 1 to plus 1 y left, right. If calculate the total minus left is right. If forward return right. If to shift to right. Okay. Number if we for 2 columns, if we shift this column inside, there's no way that we can make a more water container. Cut it here. Right. This one there. Right. We have to return the maximum amount of water. So this one, this one, water, here. Um, right, left, 3 to the left, left, me, left. So this, à try this example. Here we have initialize 0 and 3. For the first roof, three. 3, 2. One, two, three. One, two, three. Come on, let's check this. Left navigation. No, we have to check here. Okay. you have an given ref and try between the graph. Okay. Dẫn đấy. Mark left and mark right. For this, gonna be an overflow here, right? That's it, very good. Here. It's kind of like return the maximum area of below the bar is equal this plus add this or only this. 9 1 2 3 4 5 6 7 okay. Okay. I think here. Let's go here to 0. We found 1 by 1. last look up. Last index. Just hate it's just right. Yes. Now just for light image. This one. Is it just one time, right? Two to three. List. List A. Three. We can do to zero. Then we can travel with here. expand the draft. For this, we're gonna expand the draft. Okay, if right, number left. Just right and just rotate here. Start the weather. Right. Rise. Cool. Response claims, and now we move shift this left right here. This one, right? Case. Okay, this. Return. Okay, we're gonna try it. A sample here. Try it around here. for the first here, if left, okay, then now is then okay, this one it's gonna be right here two. Let's put the font here. So right now two. No. Wait, I need to use. It's gonna be no. Here. 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 Two, and now right here greater than left. So let's put here now. Let's put here. So we two. Left now is go to two. Three. Left here to right here. Now right. Continue left. Yes. It's gonna be two, 0, and left, right, here. Okay. So no. There's some problem here. 10 is left. Right is left. This rest two. It's gonna be here. It's 5. It's gonna be 7. Here 7. Okay. Now right here is equal to this one, so it's gonna be 9 and 10 now is equal to 0. Left and right, left is gonna be here. It's gonna be 1, 2, 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 8, and now that's right. Come on, come here. 10 is gonna be to this to 0. take this one, right, go here, the last element. One, two, three, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 10 is gonna work. Come on. 6. Okay, yeah. This. For the last one, we move to this. this one.
Step into Wix Studio and handle every part of your build from one platform. Map out your project with an AI-powered visual sitemap.
Hey everyone, welcome back, and let's write some more neat code today. So it's been a while for me, sorry I've been pretty busy, but let's today solve LeetCode 42, trapping rainwater. So we're given an integer array representing the heights of certain elevations or whatever, right? So it's a one-dimensional array. The first value is 0, meaning a height of 0, so that's over here. It's given an right, like we're here able to trap. And it's actually pretty simple, right? Take a look. So here we have one block of water. What if I added a second block of water? Well, we can see that there is a boundary on the right. This is good, right? But what about the left side? There's no boundary over here, right? Meaning any water I add is just going to spill out. The boundary only has a height of 1. So we're seeing that the height on the left is 1, the height on the right is 2. So we need to take the minimum of that. We need to take the minimum of 1 and 2 because that is our bottleneck. That is what's determining exactly how much water we are able to trap per position, right? For every single position, we need the max height on the left
and the max height on the right, left, and right, and then we need to take the minimum of those two. Let's take a look at this position. Clearly, we can't trap any water here, but why exactly is that the case? Well, when you look at the right position, right, in the entire right section, the maximum height is a 3, right? So that's good, 3 here. What's the maximum height on the left side? It's a 1, right? This position is a 2. If we take the minimum of 1 and 3, we get 1. So that's our boundary. That doesn't mean we can trap any water here. We can trap 0 water here. The reason is because the actual calculation is we're going to take the minimum. We're going to take the minimum of the maximum left height and the maximum right height. We're going to take the minimum of those two, and we're going to take the height that we're currently at, right? So let's say h of the index I that we're at. So this is the equation we're going to use to determine at every single position I, let's say this is our I position, right? So you can see I is in this equation. This is going to determine how much water we can trap in position I. So we know the minimum of the max of the left and right, right? Because the left was 1, the right was 3. The minimum of those is just going to be 1. And h of I, so the height at position I is 2 over here, right? 2. So we're going to take 1 minus 2. That's actually going to give us a negative number, right? That's going to give us negative 1. But we know we can't trap negative water, right? So we're always going to round up. We're never going to use negative numbers because it doesn't really make sense to trap negative water over here. So really, since the solution is negative, that really means that we can trap 0 water in this position. But let's just move to a couple more positions before you probably get the idea. So over here, right? In this position, the height is 1, right? And the max height on the left is 2. The max height on the right is 3 again, right? So we take the minimum of 2 and 3, so we're going to get 2, right? 2 is the minimum. And height of I is 1, right? The height at this position is 1. So that means we can trap exactly 1 water in this position, right? Clearly that is the case, right? We're trapping 1 unit of water. And basically, if you did this exact same calculation for every single position, including this position, you'd get the appropriate water count. So this position would give us 2 units of water. This is going to give us 1. These are going to give us 0. This is going to give us 1. And the rest are going to give us 0 water that we can trap. Once we take the sum of all those, we are going to get our answer 6. So now let me actually show you the efficient ways to solve this problem. Okay, so I'm going to show you 2 different ways to solve this problem. Both of the solutions are linear time solutions, right? So big O of n is going to be the time complexity of the solution, but the first solution I show you is going to actually require big O n of memory as well. There's an actual optimization you can do with 2 pointers to reduce the memories from linear memory, big O of n, to constant memory. So I'm going to show you both of the solutions, and it's actually not a lot of code. The code is actually pretty easy. Since for every single position, right, to know how much water we can trap both of the solutions, and it's actually not a lot of code. The code is actually pretty easy. Since
It's kind of pretty easy. Trapping rainwater. Trapping rainwater.
So for every single position, right, to
For every single position.
know how much water we can trap at index I, we need to know what's the max left and right height of every single position, right? So for this position, the max on the left is going to be 2 right over here, and the max on the right is going to be 3 right over here, right? So we're going to need to be doing that calculation a lot. So we can actually make an array and then store that calculation for us so that we only have to do it a single time each. So first we can scan
through the array, right? Just go iterate through the entire array, calculating every single max left position, meaning for this position, what's the max height on the left of it? Well, there aren't any heights on the left of it, so it's going to be 0. What's the max height of this? Well, the max height is 0, right? That's the only height that came before it. What's the max height on the left of this? Well, it's a 1, right? So we can do this in linear time, big O of n time. So I'm just going to do that, right? What's the max height on the left of this? 1, max height on the left, because there's nothing to determine how much water we can values for this position, right? 0, we want the minimum of these two values, right? Because the minimum is going to help us determine how much water we can trap in this position, right? And clearly, we can actually find the minimum of these two arrays as well in linear time. So here, the minimum is 0, minimum is 0, minimum is 1, 1, 2, 2, 1, and 0. And so now for every single position, we're going to determine how much water we can trap. And we can do that, remember, with our calculation, we can take the minimum of the left and the right and subtract from it the height at position I, right? We're always going to round up. We always want it to be greater than or equal to 0. And then we can add the sum of all of those values and then get the total water that we can trap. So in this position, we have 0 minus 0 minus 0, right? So here, the amount of water we can trap is 0. Here we have 0 minus 1. That's going to be negative 1, but we don't count negative, so the amount of water we can trap here is 0. Here we have 1 minus 0. Any water here, plus 2, plus solution. We're not going to need any of this extra memory that we pointer here. So the right pointer is going to be all the way at the end of the input array. So we're going to have our 2 pointers initialized. We're also going to have 2 variables, max left and max right, which are going to be keeping track of the maximum left pointer and maximum right pointer so far. So you can see left is initially 0, so the max so far on the left is 0. You can see right is initially 1, so the max on the right so far is 1. So now we are going to have to update our pointer. Now, which pointer are we going to shift? We're going to take the one that has the smaller max value. So right now you can see max left has 0, max right has 1, so we're going to shift the smaller one, which is left. So we're going to take our left pointer and shift it. So now our left pointer is over here, and just FYI, we know that we can't have any water stored on the endpoints, right? On the left and the right positions, we can't have any water. Our left pointer is over here, and just FYI, we know that we can't have any water stored on the endpoints, right? On the left and the right positions, we can't have any water because they're endpoints, right? They can't contain any water. But this position technically can have some water. And how are we going to determine that? Well, we're going to take our how much water this can contain, right? We're going to take the max left value that we have in our variable right now, right? How come we don't need the right value? Well, I'm going to show you. So this is the part that you kind of need to notice the trick, I guess, right? So we're in this position, right? Now, remember originally we wanted the minimum down here. You can see we wanted the minimum of the max left and max right. Well, we know what the max left is so far, right? The max left is 0, right? That's what's over here. Now, we technically don't know what the max right is, even though this variable says 1. Yes, so far it's 1, but we know that the max right could actually be 3, right? That's what the true max right is of this position, right? Because there's a 3 over here. So why is it that we don't need that value? Because remember, we want the minimum of the max left and the max right. Now, we clearly know that the max left is 0, right? So it's smaller than what's even at this position, right? And we want the minimum of it. So no matter how big this value is, right? Right now it's a 3, it could be a 10, right? It doesn't matter how big it is because we want the max of the left and the right, and we already know that the left is pretty small, right? It's 0. So it doesn't matter what's in all of these values because we know that the max left is our bottleneck, right? Remember, we shifted our left pointer from here to the next position because left was smaller than right. That's why we shifted it. That's how we're able to calculate the water that's trapped in this position without knowing what the max right is. So with that being explained, let's actually go through this so we can get to the code. So what's the amount of water that we can trap over here? It's actually 0 because the max left, which is the value that we I've solved a lot of leak.